Hi, I've been working on this project recently, and I wanted to showcase it because it combines backend engineering, real-time computation, and an interactive front-end interface. This project is a satellite tracking platform that allows users to track satellites in real time, explore satellite data, predict satellite passes, monitor conjunction risks, and compute Doppler shift for communication frequencies. First, I will briefly explain the technologies used in this project. The backend is built using Java with Spring Boot and follows a layered architecture consisting of controllers, services, repositories, and background schedulers. The application uses PostgreSQL as the database, and Flyway is used to manage database migrations and schema versioning. The system works with satellite orbital data called TLE, which stands for two-line element data. These elements describe the orbital parameters of satellites. The platform fetches this data from external sources such as N2YO, which stands for Need to Know Your Orbit, along with Spacetrak and Celestrak, which are commonly used satellite data providers. Each satellite is identified using a NORAD ID, where NORAD stands for North American Aerospace Defense Command. This identifier uniquely represents satellites in orbit. To calculate satellite positions at any given time, the system uses the SGP4 algorithm, which stands for Simplified General Perturbations Model 4. This model is commonly used for predicting satellite orbits from TLE data. For the front end, the user interface is built using React with TypeScript using TSX components. The front end communicates with the back end through REST APIs and provides an interactive interface to visualize satellite movement. Now I will briefly walk through the main features of the platform. The first section is the dashboard. The dashboard shows a live orbital display of satellites on a world map. It visualizes the current satellite position and also displays the orbital path so users can see both the past trajectory and the predicted path of the satellite. On the side panel, we can see important orbital information such as latitude, longitude, altitude, speed, and orbital period. This data is continuously updated using the orbital propagation model. The next section is the satellite database. This page allows users to browse and search satellites by name or NORAD ID. Satellites are grouped into categories such as ISS and space stations, navigation satellites, weather satellites, and scientific satellites. From here, users can select a satellite and start tracking it. Another important feature is pass prediction. Users can either use their current location or manually enter latitude, longitude, and altitude. Based on this location and the satellite's orbital parameters, the system calculates upcoming satellite passes and filters them based on conditions such as minimum elevation angle or visible passes only. The platform also includes conjunction risk monitoring. A conjunction occurs when two satellites pass very close to each other in orbit. This module scans satellite trajectories within a 24-hour screening window and detects potential close approaches. Another feature is the Doppler calculation module. When a satellite moves relative to a ground station, the transmitted radio frequency changes due to the Doppler effect. In this module, users can enter the transmission frequency and their location, and the system calculates the expected Doppler shift during the satellite pass. Finally, the platform includes a notification and alert system. Users can configure alerts such as satellite pass alerts, conjunction warnings, TLE data alerts, and re-entry warnings. Background schedulers continuously monitor these events and trigger notifications when conditions are met. Overall, this project demonstrates a full-stack system combining Spring Boot backend services, orbital mechanics calculations, external satellite data integrations, and an interactive React TypeScript frontend for visualizing satellite movement in real time.